Any discussions about how to deal with the emission problem from fossil fuels will sooner or later end up turning to hydrogen. Hydrogen is a tempting alternative fuel that has been in the limelight for decades now. However, difficulty in production and storage, along with inefficiency, has stopped it from being a game changer. But the tables are starting to turn. There's news from all over the world about potential breakthroughs related to the production of green hydrogen. The names worth mentioning are an Australian-based company, Hysata, and the Korean Institute of Science and Technology, which have devised new electrolysis methods for preparing green hydrogen in a more efficient way. Too much information in a single sentence, right? Don't worry, we will be talking about all the details of these recent hydrogen breakthroughs, and we'll also be looking at future planning. Let's start with some basic information. Hydrogen is the first element in the periodic table. Despite being one of the most plentiful elements in the universe, extraction of pure hydrogen is a complicated process. Hydrogen is obtained by electrolysis of water, which is the working principle of fuel cells. Fuel cells work just like batteries. Hydrogen is fed to the anode, oxygen is fed to the cathode in the presence of platinum electrodes, which produces electricity. These fuel cells can be used to power anything that uses electrical energy. NASA rockets that are launched into space provide electrical power through fuel cells. It produces water as a byproduct, which is so pure that even astronauts can drink it safely. Hydrogen is also used to power hydrogen fuel cell vehicles, which are more efficient than an internal combustion engine fueled by gas. But the downside is electrolysis is a very time-consuming and expensive process. Also, the system is super inefficient. It takes more energy to produce the hydrogen than you get out of it. Transportation is also a factor here. Unlike gasoline, gasoline has a lower density, so it needs to be compressed first before transporting. Today, 1,600 miles of hydrogen pipelines deliver gaseous hydrogen around the US, but that is not enough infrastructure to encourage widespread use. That's why it always lags behind lithium-ion batteries in the EV industry. There are other processes of making hydrogen too. The method of production using fossil fuels, such as propane or gasoline, results in the formation of gray hydrogen along with huge amounts of carbon dioxide gas. When this CO2 gas is captured and stored elsewhere, then the produced hydrogen is called blue hydrogen. And finally, hydrogen produced from the previously discussed electrolysis process is called green hydrogen. According to a recent study, currently, gray hydrogen costs about $1.84 US per kilogram. Blue costs $2 to $3.5 per kilogram, and green costs $4 to $6.5 per kilogram. So you can clearly see gray and blue hydrogen are most cost-effective, but they don't make the fuel entirely green. However, there's no need to be frustrated. Revolution is just around the corner now. Hysata's new capillary-fed electrolyzer brings a fresh new take to technology itself. According to a report in the well-known scientific journal Nature, Hysata has produced an alkaline capillary-fed electrolysis cell that has the capacity to liberate green hydrogen with an efficiency of 98%. That number is bigger than International Renewable Energy Agency's 2050 target and significantly better than existing electrolyzer technologies. The company is also the first in the world to commercialize a capillary-fed electrolyzer. But how did this happen? Well, the problem with hydrogen is its size. We are trying to stop the smallest element in the universe from losing potential energy in any form during electrolysis. For years, scientists have been trying to stop this energy loss, and it looks like Hysata has now found the real culprit. In the process of electrolysis, due to the presence of oxygen, the air gets trapped inside water and forms bubbles. Since bubbles are filled with air, they don't conduct electricity, and when these bubbles get attached to the surface of the electrodes, they disrupt the electrolysis process, making the system inefficient. Therefore, the research team at the University of Wollongong invented the capillary-fed electrolyzer. In such an electrolyzer, the liquid, in our case water, is kept in a reservoir at the bottom of the electrodes. The water is kept out of the reach of the electrodes in the beginning. Gradually, the water is drawn through an inter-electrode separator due to a change in pressure. This is the capillary action part of the whole system, which eliminates any kind of bubble formation in the separator, and thus hydrogen and oxygen can liberate without any energy losses. Think of it as drawing out the juice from a glass using a straw. Yes, it's that simple, yet such a groundbreaking invention. Talking about the design, the company's electrolyzer is 5 times smaller than a traditional alkaline electrolyzer and contains 20 times less liquid. According to Hysata CEO Paul Barrett, the electrolyzer cell frame is made using a low-cost and scalable technique. With commercial shipment and mass manufacturing, these cells can produce green hydrogen for less than $1.5 per kilogram. Barrett said, "Our technology will enable hydrogen production of below $1.50 US per kilogram by the mid-2020s, meeting Australian and global cost targets much earlier than generally expected." But Hysata isn't the only one who's making headlines. A team from the Korean Institute of Science and Technology has developed a new anode exchange membrane, AEM, electrolysis technology. The technology promises lower costs, higher performance, and 10 times greater durability than any previous AEM technology. Typically, electrolyzers use proton exchange membranes, PEMs. It is a membrane designed to separate cathode and anode. The members allow the passing of positively charged ions that are attracted to the cathode. Here, the positively charged hydrogen ions gain electrons and hydrogen gas is liberated at the cathode while oxygen is released at the anode. That sounds quite good, but the issue here is materials. PEMs work in an acidic environment and, to stand the harshness of that environment, highly non-reactive and expensive materials are required. Ruthenium iridium or titanium are used as electrodes. Platinum is also used as a catalyst to increase the electrolysis rate. Therefore, to produce green hydrogen at a vast scale, the manufacturing costs need to be cut down. One alternative electrolysis technology being researched is anion exchange membranes. AEMs work in a different fashion, and they allow negatively charged hydroxide ions to liberate at the anode, while hydrogen ions gravitate towards the cathode, finally producing hydrogen gas. AEMs can work properly in an alkaline medium, so they don't require fancy metals, reducing the cost by about 3,000 times. However, they haven't been brought to the public's attention because of their lack of durability and efficiency. Now a team from the Korean Institute of Science and Technology, KIST, says it's tested a new membrane and electrode assembly that outperforms prior AEMs by a factor of 6 and outlasts them by a factor of at least 10. Also, it has 20% more efficiency than standard PEM technologies. In a press release, they said, "The developed material represented excellent durability of more than 1,000 hours of operation and has achieved a new record cell performance of 7.68 area centimeter squared. This is about 6 times the performance of existing anion exchange materials and about 1.2 times that of the expensive commercial PEMWE technology, 6 area centimeters squared. Generally, PEMs last somewhere in the region of 50,000 hours or 5.7 years. KIST-developed AEMs have surpassed the 100-hour lifespans of existing AEM electrolyzers. But still, they haven't been able to show superiority or equality to traditional PEMs when it comes to durability. However, these electrolyzers have managed to take the lead in terms of performance. A few more years of research might solve this durability problem. Even though the news is game-changing, the new contraptions are still under development. What about their future? Well, Hysata is already on a roll. Their original cell architecture was designed to be mass-produced in the first place. The cell itself is injection moldable and other core parts are made up of existing technologies. Furthermore, their electrolyte cells don't require precious metals to function. The team is working on 5 megawatt cells modules and mass manufacturing is expected to start in 2025. Speaking of KIST, the researchers say that further improvement is necessary for the cell to be mass-produced. Still, the new membrane material may find other uses in the meantime. To summarize today's video, Hysata has developed a new electrolyzer cell that can produce green hydrogen with an efficiency of 98%. Parallelly, a team of researchers from the Korean Institute of Science and Technology has developed a new anode exchange membrane that can outperform existing ones up to 20% in terms of affordability, durability, and efficiency. Green hydrogen has the potential to play a key role in tackling critical energy challenges. And with these recent breakthroughs, it looks like we are progressing rapidly toward a sustainable and bright future. That's it for today's video. If you have enjoyed watching, be sure to leave a like and subscribe to our channel. Until next time.